In a normal distribution, which is greater, the mean or median? Now, in a normal distribution or a bell-shaped distribution, the mean, median, and mode are all equal. They don't mention the mode as well, mode here, but the mode is also equal to the mean and median. Determine whether the graph can represent a normal curve. If it cannot, explain why. Now, we've drawn a lot of normal curves while we studied the empirical rule. And remember, normal curve always has to go. Let me draw one more. Normal curve always has to go. So if this is the horizontal line, then the normal curve always needs to go like this. It keeps getting flatter, and this is not strictly correct. So it keeps getting flatter and flatter. It never hits the horizontal axis. So it keeps getting closer and closer. It has the horizontal axis as its asymptote, and it never comes back. So it reaches its peak, it comes down, 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 down. But once it starts going down after hitting the peak on either end, it never returns. So the picture shown is not a normal curve, because here after going down, it's coming back up again. And the same over here. So let's see which one captures it. No, it's not normal. Cannot represent a normal density function because it is symmetric. No, normal curve is symmetric. So just because it's symmetric is not the reason why it's not normal. The reason it's not normal is that it's bouncing back up. Cannot represent a normal because it increases as x increases, very large or very small. Yes, that's the reason, because as x increases in this direction, the curve starts increasing, which should not happen, because we know that as x increases, it should keep becoming more and more flat and decrease towards zero instead of increasing. Same here on the other side. So C is the correct reason. Similarly, this is not a normal curve because it has to have the horizontal axis as the asymptote, whereas here the asymptote is like quite a distance up from the x-axis. So let's see which one captured, because it is no inflection points, that's nothing to do with it. The graph cannot represent a normal density function because it's not bell-shaped. Well, actually it is bell-shaped, and yet it's not normal because of the reason I mentioned. Can represent a normal density function? No. So now we know this is correct, but let's look at the reason. Cannot represent a normal density function because it does not approach the horizontal axis as x increases or decreases. Remember, normal curve has to approach the horizontal axis. See, this one is approaching the horizontal axis. If we enlarge the horizontal axis a bit further, similarly in that direction. So okay, now this is not normal because it's not symmetric. So let's see which one says that. Represents a normal because as x increases without bound, the graph takes negative values. No, it's not taking any negative values because it's bimodal. No, it's not bimodal. Just this point is the mode. It has one mode. Normal density function because it's not symmetric. Yeah, that's the reason. Normal curve has to be symmetric. What's the area, total area under the normal curve? So the total area under any probability curve is 1, whether it's normal or later on we'll study T curve, and we'll also study the chi-square curve. Under area under all of them is 1. And actually earlier in this section we studied the uniform distribution, and I was explaining to you that the area under the curve has to be 1. Remember when we were looking at those rectangles and squares in the earlier problem number 4. So under any normal probability, any probability curve, whether it's normal or not, the area is 1. So this is the analog of saying that the sum of probabilities is 1, like we had in a discrete distribution. Normal distribution is continuous. So here the analog of the sum being 1 is the area under the curve being 1.